Okay, guys, so today you're going to learn how to do 3 different hypothesis tests called chi-square test, or some people call it chi-square, whatever you want. It is chapter 25 in our textbook. You will need these notes, save them to your computer, and then you will need a calculator, obviously. So let me start the PowerPoint that has the answer key. I guess first we can just, let's just go through the PowerPoint. F5. Okay, chapter 25, chi-square test. So basically now for the next hypothesis test that we're doing, your data are going to be counts of categorical variables. So you'll see them. They're tables that just have counts, like the number of people with blue eyes or the number of blue, green, red M&Ms, whatever. This is called your new test statistic. It's no longer a z-score, it's no longer a t-score. Now it's something called a chi-square score. So that's what it's called. It's called a chi-square. Or like I said, chi-square, whatever you want to call it, chi-square. This is the formula for the chi-square. The O stands for the observed count, so like the number of observed items, minus E, which stands for the expected count, squared over E. And we're going to do an example in a minute. These are now the conditions that you would be checking when you're doing a chi-square test. You're still going to be doing like the randomization condition, the 10% condition, but now there's like an extra first condition here that just says the data that is given to you is count of categories. So we'll have to check that one first. The data that is given to us is count of categories. And I'll show you an example when we get there. Your sample still needs to be randomly selected. Your sample still needs to be less than 10% of the population. And your sample still needs to be large enough. But now here's another one that's different. For the large enough now, here's what you'll check. You will just have to check that your expected counts are at least 5. Expected counts are at least 5. So those are the conditions that you would check for the hypothesis test that we'll do today. Okay, so I guess here's some facts that you should know about the chi-square distribution, because you will see these as multiple choice concept questions. Here it goes. The chi-square distribution does have degrees of freedom, like the t-distribution did. Next, the chi-square distribution is always skewed to the right. Finally, the chi-square distribution only has positive values. And lastly, as the degrees of freedom increase, your chi-square distribution will become more and more normal. So here's some pictures. Okay, this is a chi-square curve. So notice how it's skewed to the right completely because the degrees of freedom was only 1. Here's another chi-square curve. Again, skewed to the right because the degrees of freedom was just 2. And then here's another chi-square curve. They're always skewed to the right and only with positive values. So you notice how they start at 0 or higher. So these are the chi-square curves. I guess I forgot to include like at least a degrees of freedom of 30. Then it would look more like a normal curve if the degrees of freedom was 30. But somehow I skipped it. That's fine. All right. So today you're going to learn 3 types of chi-square test. Number 1, goodness of fit. Number 2, homogeneity. Number 3, independence. So I guess let's keep going. Steps of doing a chi-square test. Let me see. I think everything is written on your notes. Yes, they're written on your notes there. So step 1, we're going to write some hypotheses. I'll teach you in a second. Step 2, you're going to check those conditions that I just talked about. Step 3, we're going to use a calculator to find our test statistic and p-value. And then last step is always make your decision and conclusion based on your small p-value or not. So I think it's just best if we go straight to an example. What the? Sorry. I think the PowerPoint had like a noise. I don't know. Ignore that. Okay. Anyway, here we go. First type of test. It is called a chi-square test of goodness of fit. So the goodness of fit test allows you to take like one sample, like it's only one sample, and you want to see how well it matches or it fits the population expected sample. So that's what we're about to see. We want to see if the sample that you collected, which is the observed count, would match or fit what is expected from the population. Oh my goodness. All right. So here's the first step you'll need for your chi-square test. You would need to write some hypothesis, and just like it's written in your notes, the null hypothesis for a goodness of fit will be that your sample is the same as expected, or you can just say your sample does fit the expected population. So that's what we assume. The alternative is we want to know, or we want to test and see if the sample is any different than what is expected from the population. So that's what we're about to write on example 1. And then finally, last thing you'll need for the goodness of fit before we get started with the example is your degrees of freedom are going to be n-1, where n is the number of categories and not the sample size. So you have to remember that for chi-square test, n is the number of categories and not the sample size. Not the sample size like it was for the t distributions. Okay, so that's a lot of talk. Let's do an example. Number 1. I guess I'll just read it. Example, most computer software companies provide a telephone number that customers can use to obtain technical assistance. A particular manufacturer recently changed from a toll-free number to a, 1-800 number. The distribution for the lengths of calls in seconds when the number was a toll call is given below. So this is the distribution of the population, like 13%, 21%, 40%. This is the distribution of the population when the number was a toll-free number. Now it says, after changing the number to a 1-800 number, a random sample of 300 calls was collected, and the length of calls was recorded. So now here's a distribution of your sample. So this is the sample of 300 calls. And now you want to see how well your sample matches the population. So you want to know if it fits, or you want to know if it's any different than what was the population expected values. So the question is there sufficient evidence to conclude that there has been a change in the distributions of lengths of calls now that you've switched from the toll number to a free number? So basically, does this sample, is it any different than what was expected from the population? So get your calculators ready. And I guess first we need to do some writing. Step 1, we need to write some hypotheses. The null hypothesis for a goodness of fit test, you could just write our sample fits or matches the expected population. Or like I wrote here, HO. The distribution of calls for the free number is the same as expected. The wording doesn't have to be exact. These are going to be multiple choice anyway, so it just needs to sound right. So one more time, the null hypothesis would just be that your sample distribution matches or is the same as the expected population distribution. That's always your null hypothesis for a goodness of fit test. The alternative would just be that your sample distribution is different than the expected. So that's what we were trying to test. And that's called a goodness of fit test with your null and alternative hypothesis. So that was step 1. Write the hypotheses. Step 2 is going to be to check those conditions I talked about. So the conditions are the randomization condition, 10% condition, large enough condition, and that first one now called the counted data. Let's go. And it looks like I skipped the counted data condition because obviously these are all chi-square tests. You can write it if you want to, and maybe you should just in case it's multiple choice, but technically my first condition here should just be counted data. So that just means that the data that we have here, 27, 33, 93, 88, 59, that's our sample. Those are counted values, like 27 calls lasted from 0 to 199. 33 calls lasted from blank to blank. So these values are called counted numbers. So I guess that's what I should put for my first condition here. Counted data condition. The values we have are counts for categories. I'll try to fix my PowerPoint. So counted data condition. The values we have are counts for the categories. The next condition is the one that you've always known, randomization condition. The problem says we have a random sample of 300 calls. 10% condition, assume that 300 is less than 10% of the population. And okay, for the large enough condition, I need to teach you how to do that. First, write that down while I add my counted data condition here. Okay, I think I can put it. Counted data condition. We have counts for the category. Okay, I think okay, so I added that counted data condition. So we have counts for the categories, and then I already did randomization and 10%. Okay, so now we'll need a calculator for the large enough condition. So according to your notes, the large enough condition is that your expected counts have to be at least 5. So let me show you how to get those. All right, so here, I guess you're gonna have to make a little table to show the expected counts. So let's make a little table that has the length of the calls. So put all the categories, 0 to 199, 200 to 239, 240 to 359, 360 to 479. And I'm assuming those are like minutes or seconds. I don't know. In seconds, these are seconds. Well, yeah, you wouldn't want minutes. So seconds. And then the last one is more than 480 seconds. So make the little table. And now let me show you how to get the expected counts. So, okay. So the way you get the expected counts. The table that is given in your problem are called observed counts. So these numbers here, 27, 33, 93, 88, 59, those are called observed because that's how many calls you actually observed in your sample of 300. So those are called observed. I don't know, label it O for observed. Okay, now here's how you get the expected counts. So if you take 300 calls, your expected counts come from these population percentages. So out of the 300 calls, you expect 13% of them to last between 0 and 199 seconds. And then again, out of the 300 calls, you expect 21% of them to last between 200 and 239, and then so on. So this is how you get those expected counts. You'll take what I just said. You would take 300 times the population expected percentage of 13%, and then you'll take 300 times the 21%, 300 times the 40%, 300 times the 19%, and 300 times the 7%. And I guess I did it right here at the end. You can just copy it down if you want to go a little faster. But if you do use the calculator, this is what you would get. You would get 39 for the first category, 63, 120, 57, and 21. So you will definitely need to know how to calculate expected values for your, for your next term assessment. So make sure you know how to get these expected values. And then I would label these as expected values. So these are your expected counts. So in this sample of 300, this is what we would have expected from the population. And notice how all of those expected counts are at least 5. So yeah. So finally, step 2, done. I have checked all of the conditions. Make sure you know how to calculate expected counts based on the population proportions. Step 3, let's now use the calculator to find our test statistic and p-value. Okay, for starters, here's the formula. I guess I'll show you how to do it by hand first, and then we're just going to use the calculator to confirm or to do it faster. But basically, the formula for your test statistic is, like I told you earlier, it's called a chi-square. The way you would find it is you have to take every observed count, subtract its expected count, square it, and divide it by expected count. So, so here's an example of, let's just do one calculation by hand. The rest we'll use the calculator. So if I did want to find this chi-square value, I'm going to first do the first O minus E squared over E. So you need to take, okay, here goes. You need to take your first observed count. So let's start with the first category of 0 to 199 seconds. So take the first observed, 27, minus the expected, 39. 27 minus 39 square over 39. So that would be the first value. Okay, then you need to do all the other ones because the little summation thing means to add them all up. So then we would have to do it again and take 33 minus 63 squared over 63. Obviously, I'm going to teach you how to do it on the calculator because it will go way faster, but this is how you would show your work. And then you would do it again, plus 93 minus 120 squared over 120, plus 88 over 57 squared over 57, and then plus the last one, 59 minus 21 squared over 21. So notice how I only showed like the first substitution, and then I just did plus dot, 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 plus the second substitution. So now finally get the calculator ready so I can show you how to do it on the calculator. So calculator. What you're gonna need on your calculator is you're gonna need to go to a spreadsheet, and in the spreadsheet, so go there, spreadsheet. On the spreadsheet here, you're gonna have to type in the observed values and the expected values. So let's do that. Take your table and put in the observed values. Where were they? Let's find it. All right, so the observed values were 27, 33, 93, 88, and 59. So those were the observed values, the ones that were given to you at the very beginning. I like to call them O for observed. And then on the second column of your spreadsheet, you're going to have to type in the expected values that you calculated. So remember the expected values that we did, like 300 times 13%, 300 times 21%. So if you didn't write them down, here they are. The expected counts were 39, 63, 120, 57, and 21. And again, I would label those as E expected. Once you have typed in your observed counts that are given and the expected counts that you calculated, now the calculator will do the rest for you. It's called a chi-square goodness of fit test. So try to find it. Don't forget to label it O for observed, E for expected. So the way you find the chi-square is menu, statistics, test, and on the calculator it's called chi-square GOF, goodness of fit. That's the one we're doing right now, GOF. So click on that thing and follow the steps. It's going to ask you, where is your observed list? Remember I called it O for observed? Where is your expected list? I called it E for expected. What are your degrees of freedom? The degrees of freedom for a GOF is N minus 1, where N is a number of categories. So if you look at your table, we've got 1, 2, 3, 4, 5 categories. So your degrees of freedom should be 5 minus 1, 4. Where do you want your results? You can just leave it like that. And the calculator has done all the adding for you, and it has come up with your chi-square value, which is a huge number here, 109.67. So that's what if you were to do this calculation by hand and add them all up, that's what you would get, 109.67. Next, the calculator has done the p-value for you. And be very careful because it's not 8.5. It's actually like 8.5 times 10 to the negative 23. So basically 0. So we'll write down the p-value, but I need to show you how to calculate p-values just on their own, because that's on your next assessment for term 4. So this is the p-value. I'm going to show you how to do it anyway. Let's see, does this show me? Yeah, it does show you. Okay. So the way you calculate a p-value is by finding the probability that a chi-square is greater than the 109.67. This is always going to be greater than, because your chi-square is always skewed to the right and only positive numbers. So this will always be a greater than symbol here. So now the way you would do this by, like, on the calculator, you need to know how to do this separately for different questions. But the way you would find the area here is kind of like you did with the normal CDF and with the TCDF. This time, go find something called a chi-square CDF. It's called a chi-square CDF. So let me show you how to do it, because you need to know the skill on the quiz and test next term, I guess, if you still care. But let's go just do a regular scratch pad. Okay, so on the scratch pad, you need to find a chi-square CDF under distributions. Menu, probability, distributions. It's the one that says chi-square CDF. The lower bound is that 109.67. The upper bound will always be positive infinity because it's just always greater than. And then, like I told you, the degrees of freedom was 5 minus 1, so 4. So make sure you know how to do this skill, chi-square CDF. It will be on your next term 4 assessments. So there it is, 8.5 times 10 to the negative 23, which we already knew from the calculator because it already did it for us, the 8.5 times 10 to the negative 23. So that's basically almost 0. Okay, so those are what? Now that you're done step 3, found the test statistic and found the p-value, your last thing is the same as always. Make a decision and make a conclusion. That p-value is almost 0, so you can reject the null hypothesis and conclude that the distribution of length of calls has changed. So basically, let's answer the question. Chi-square table. Before there were calculators, there used to be these tables, but we don't do those anymore. We have a calculator now. All right. Since my p-value was so small, I rejected it at 2% or 1%, or I guess 2% because that's what the example said. I rejected the null hypothesis, and therefore I do have evidence that the distribution of cost has changed. I'm going to pause for questions, and then we'll do one last example, which is the other chi-square test. Okay, so now that you've done the goodness of fit test, here's the good news. Technically, there's two other chi-square tests left, which are the chi-square test of independence, and then there's the chi-square test of homogeneity. So there's two different ones, but the good news is they're actually the same test. Like the procedures will be the same, the math will be the same. The only difference between these two tests is going to be the hypotheses that you write and the conclusion. So let me just tell you, for an independence test, your hypothesis would be that, null hypothesis would be that your variables are independent of each other. The alternative would be that the variables are dependent on each other. And we'll do an example in a minute. And then, like I said, for the homogeneity test, when we get to that one, it's pretty much going to be the same thing, except for the hypotheses are worded slightly different. For the homogeneity test, the hypotheses are worded as null hypothesis. The populations are the same, and the alternative is the populations are not the same. So let's just do one at a time. Let's do independence. So the chi-square test of independence is to see if there is an association or a relationship between two variables. So for this one, you take one single random sample, but you divide it into categories for two separate variables. So on this example number two. Okay. Example number 2 says a study was compared for non-combat mortality rates for the U.S. military personnel who were deployed in combat situations, and then those who were not deployed. So that's our first variable here. You want to know if the military personnel was deployed to combat or not deployed. So that's one variable with two categories. Your other variable is they wanted to compare the mortality rates, so the cause of death. That's your second variable. So the cause of death was either unintentional injury, illness, or homicide, suicide. So just very sad here. So this is called this is called two variables. So we don't do the GOF. We do the independence because the question wants to know, it literally says the word independent here. It wants to know, is there evidence that the cause of death is independent of whether they were deployed or not? So for this one, if you see the word independent, then that means independence test. Or like if you see the word associated or related, then those are all the same kind of independent test. So here's how you do it. Step 1, write your hypothesis. The null hypothesis for an independence test is that the variables are independent. So you can just put variables are independent, or I put cause of death and deployment status are independent. For short, just put variables are independent. The alternative would be the opposite. The variables are related, so not independent. So that is step 1. The hypotheses are independent variables for your null hypothesis, and then related variables for the alternative. And now step 2 is to check those conditions again. I'm just going to read them through, and you can write them if you want to, or you can just come back and look at the PowerPoint. But we still have data counts. So yeah, that's why I always skip that first condition, because all of these are data counts. But according to your table, you still do have counts of people. Like those values are counts. So I skipped that first data count condition. Next, I guess we assume we have a random sample. Our problem says we have a random sample of 1,580 military personnel. Assume that the sample is less than 10% of the population. And now we need to check to see if the expected counts are greater than 5. I went ahead and wrote it. They are greater than 5, but here's how you check that one. All right. You need to know this again for your next test and your next quiz for term 4. Here's how you check expected counts when your data is in a table like this, a two-way table. Here goes. Expected count. There is a formula for the expected count. Write it down on your notes because I didn't put it on your paper notes. So write it down. If you do want to find the expected counts, which you will have to next term, here's how you find the expected counts. For the expected counts on each of these little cells, here's what you have to do. Expected count equals, write it down. It equals the row total times the column total divided by the table total. So I definitely did put one of these questions on your quiz and test next term, because I was just making them yesterday. Okay, so we're about to find our expected counts. The table that is given to you on paper, those are called observed counts. So the 183, 30, 11, 784, 264, and 308, those were the number of observed people out of the 1580 that were classified or that were put into the categories. Down here, we're going to find the expected counts. So let's start with the first one. Okay, the 183 is the number of observed people who died from an unintentional injury that were deployed. So if we want to find the expected counts for the ones that died of an unintentional injury that were deployed, here's what you'll have to do. You need to take the row total. So this value here is on this deployment row. So that would be 224. And you need to multiply it by the column total. So again, this value here is under the unintentional column, so 967. And then you're going to divide by the whole table total. So I think, did I show my work? Let me see. Yeah, I showed it right here. So once again, to get the expected count for this first cell here, you're going to do 224, which is the row total, times 967, which is the column total, divided by 1580, which is the table total. And make sure you do leave your expected counts as decimals, because that is possible. That's just the expected number of people who died from an unintentional injury that were deployed. 137.09. Round to 2 decimal places, because the test will ask you 2 decimal places. Okay, now we're supposed to just keep doing that for the rest of these, like all the rest of those, but no one has time for that. So let me just show you on the calculator how you can do it all. The calculator will do these for you. So if you want to pay attention and get your calculator, I'll show you how you can get all of these expected counts on your calculator. It's going to involve a little bit of like algebra 2 called matrices. So here goes memories of algebra 2. You need to go to the scratch pad and go to get a matrix. So the way you do that, or one way to do that, is from the scratch pad, you can click the little button next to the number 9. Just click the button to the right of number 9. And then you'll see these little matrix brackets. Click the 3x3 matrix here. That one.
What if you don't have that?
What do you mean you don't have that?
Like, you go on a second matrix. Yeah, like after we go to the second matrix, and then you go to edit, and then 1, and then matrix 8, and then 2 by 3.
Oh yeah, we need to change the dimensions of this. So what's my table? My table's got 3 columns, 2 rows. 3 columns. He helped you? So 2 rows, 3 columns. Yeah. And if you get this wrong, then you have another chance to fix it. Like if you get them backwards. Okay, I got them right. Okay, now you have to type in your observed count. 183, 30, 11, 784. Yeah, definitely come watch the video again because you're gonna forget all this over spring break. 308. And you have to save these counts, save them under an observed matrix. So the way you save it is once you type them all in, scroll to the right, you need to press Control var, which is a STO, like control store, and the little arrow will pop up. And now I like to save it under O for observed. Enter. So again, the way I saved it is I did Control Store, and then I pressed the little O. So now anytime I call O, it's going to be that observed matrix. Okay, now that you have that, here's how you get the expected counts. You're going to have to go do a chi-square independence test. So go to menu, go to menu and test, find the chi-square independence. So menu, statistics, stat test, and you're not going to see the word independence. You're going to see the one that says chi-square two-way test, like a two-way table. This is what you will use for the chi-square independence, and that's the same function that you'll use for the chi-square homogeneity. So click on that. And then all it's going to ask you is, where is your observed matrix? Remember I called it O? I don't know what you called it. And press OK. So this is going to give you a lot of information. For starters, it's going to give you your chi-square value. We'll copy that in a minute, 57.9. It's also going to give you your p-value, which is almost 0 again, 5.3 times 10 to the negative 12. It tells you here what the degrees of freedom are, 2, and I'll show you how we got that. And then it does have the expected matrix for you saved already, where it says EXP matrix. That's the expected matrix. You just need to know where to find it. So let's start with the expected matrix. So let's go find it. The way you find the expected matrix is under variables. So you have to press the button that says var right above the 9. And then just go to the one that says stat.exp matrix. That one. Stat. Press enter. These are called the expected counts. And we already did the first one, if you remember, the 137.09. So now there they are, 137.09, 41.68, 45.22. So come back and watch the video for this part and try it again. But again, you're going to first have to store your observed counts into a matrix. Then you need to go do a chi-square two-way table test. Then you need to press the var button, the variable button, and get this expected matrix. And now you can just copy it all down, I guess, if you wanted it, if you were showing your work. So here's all the little expected counts. And these are all the observed counts that were given on the problem. So that was, they're definitely all at least 5. So all the conditions are met. So all the expected counts are at least 5. So we're ready to do our chi-square number. Again, if you want to show your work, the way you will show your work is you do the observed minus the expected square over expected. So I would take like that first one, the 183 minus 137.09, I guess, square over 137.09 plus dot, dot, dot. But we don't need to show your work right now anyway, because the calculator already did it for us. Once you did that chi-square test, just copy the chi-square value right here, 51.9. 51.9. 51.9. And then same thing with the p-value. You can just copy it straightforward. It was 5.3 times 10 to the negative 12. 5.3 times 10 to the negative 12. Oh, what? Oh, hold on. Let me pause real quick. I'm coming. Let me check. Okay, Grace, I have it. You can go. I'll see you for class later. Okay. All right. So here's how you do the degrees of freedom for an independence test and for the homogeneity test. It's on your notes. The degrees of freedom is equal to, you definitely need to know this as well. It's just a simple question on your next test that asks you what are the degrees of freedom. Here they go. It is equal to the rows minus 1 times the columns minus 1. So based on your table, the table had 2 rows, so deployed and not deployed, so 2 minus 1 times the 3 columns minus 1. So 2 minus 1 times 3 minus 1 is going to be 2. That's the degrees of freedom. And then the p-value, like I said, the calculator already did it. Like, what is it? 5.3 times 10 to the negative 12. But here's how you would do it with the chi-square CDF. Again, make sure you know how to do just regular chi-square CDFs. 51.9 to infinity, the 2 degrees of freedom. And again, it's almost 0. 5.3 times 10 to the negative 12. So finally, with that p-value, make your decision and conclusion like always. So decision, I reject the null hypothesis because the p-value is so small. I do have evidence that the variables are related. So I do have evidence that there's a relationship between the cost of death and whether they were deployed or not. Which is, I guess, what I said right here. So there is evidence of an association or relationship or dependency between the 2 variables. And that's example 2. Now we're not going to do example 3 all the way because I want you to look at your test. But example 3, let me just show you that everything is the same except for the hypotheses. So again, this was called an independent chi-square test. The next one, or the last one you have to know, is the homogeneity. Everything works exactly the same as this independence. So you still do like expected counts, you still do the row times column over everything's the same. The let's skip through this. Okay. Okay, the only difference with the homogeneity test is that instead of taking one sample only, you take multiple samples. Like you take multiple samples of people. So that's the first difference. You take multiple random samples instead of just one sample. So that's the main difference between the homogeneity and independence. Independence is one sample only that was taken. Homogeneity is multiple random samples that are taken. And then the last difference between the homogeneity and the independence is the, okay, I give up. I can't mute it. The last difference is the hypotheses. For the homogeneity hypothesis, is the question is going to ask you, like, are the variables the same? So for the null hypothesis, you would put assume the variables are the same. For the alternative, you would say assume that the variables are different. So that's the only difference. The number of samples that were collected is different, and then the hypotheses are different. Everything else is going to be exactly the same. So on your own, just go through the last example on the PowerPoint, but everything's exactly the same. Like I said, the only difference is the hypotheses and the number of samples. Okay, let me pause. Let me just stop the video. Nope.